There are several types of special takeoff procedures which are used under various conditions. The first of the additional takeoff procedures is called the Contaminated Runway Takeoff Procedure. Contaminated runways pose a special hazard in takeoff, and as a result, special procedures need to be carried out. You may recall from the lesson on airfields that a contaminated runway exists when more than 25% of the runway surface area is covered by surface water, slush, or loose snow with an equivalent water depth of more than 3 millimeters. The recommendation is to avoid takeoff or landing in these circumstances, but so long as the procedures, which have been approved by the authority, are laid out in the operation manual, then takeoff and landing is permitted. The effect of the contamination on the takeoff is twofold. Firstly, due to the extra wheel drag and impingement drag, the takeoff distance increases, and secondly, because of the low wheel friction, the accelerate-stop distance increases. However, notice that the accelerate-stop distance increases by more than the takeoff distance increases. The solution to this problem is to reduce V1 and reduce aeroplane mass. Detailed on page 24 of section 4 on CAP 698 is the Contaminated Runway Takeoff Procedure. The top of the page states the procedure cannot be carried out when reduced thrust is used or when the depth of contamination exceeds 13 millimeters. The rest of the page describes in detail the methodology of the procedure and gives an example which you may want to work through in your own time. Turning the page to page 25, you can see the calculation tables for 2 mm contamination, and on page 26 for 6 mm contamination, and lastly on page 27 for 13 mm contamination. Returning to the 2 mm contamination page and working through a simple example, we can see how the reduction to V1 and the reduction to the mass is calculated. Assuming a regulated takeoff mass of 56,000 kilograms and an airfield pressure altitude of 4,000 feet, you can see that the mass reduction is 6,300 kilograms and the V1 reduction is 16 knots. However, if the depth of contamination was 6 millimeters instead of 2 millimeters, notice now that the mass reduction is more at 8,100 kilograms and the V1 reduction is less at only 8 knots instead of 16. Therefore, with increasing contamination depth, the mass reduction increases, whereas the V1 reduction decreases. Lastly, there are two important points to consider about the certified performance of an aeroplane on a wet or contaminated runway. Firstly, the use of reverse thrust is allowed for the determination of the accelerate-stop distance, whereas it is forbidden to be taken into account for the accelerate-stop distance determination on dry runways. Secondly, a lower screen height of 15 feet is used to determine the takeoff distance. These 2 points may mean that for certain aerodromes, it could be possible that the maximum takeoff mass for a wet runway could exceed the maximum mass for a dry runway. Therefore, JAR Ops 1 states that on wet and contaminated runways, the takeoff mass must not exceed that permitted for a takeoff on a dry runway under the same conditions. The second type of additional takeoff procedure is called the Increased V2 or Improved Climb Procedure. This particular procedure is used when the performance limiting mass is the climb limit mass. In other words, the climb performance is poor and is severely restricting the potential mass of the aeroplane. Before we start, it is important to understand that in the event of engine failure, the initial climb-out speed is V2. However, V2 is not the best climb angle speed. V2 is considerably slower than the best angle of climb speed, which, if you recall, is called Vx. As an example, for a typical new generation 737, Vx is 80 knots faster than V2. Therefore, climbing out at V2 produces a climb angle much less than if the aeroplane were to climb out at Vx. What the improved climb procedure aims to achieve is to increase V2 to be much closer to Vx. This will greatly enhance the climb performance. Understanding the concepts of the increased V2 procedure would be best illustrated by working through an example. On screen is an example where the field limit mass is 61,000 kilograms and the climb limit mass is 52,000 kilograms. The performance limiting mass is always the lower, and therefore the mass for takeoff must be 52,000 kilograms. This is a shame, since the runway can allow a far greater mass. Therefore, by taking off with only 52,000 kilograms would mean that there would be a significant proportion of the runway left. This can provide a clue as to the solution. With all the excess of runway, it would be possible to stay on the runway for longer during the takeoff to build up more speed. This will ensure that at rotation and at the screen height, a faster V2 will be reached, and this faster V2 will be much closer to Vx. This ensures that the climb performance significantly improves. As a result of the improved climb performance, the climb limit mass can increase, which would increase the performance limited takeoff mass and provide an improved regulated takeoff mass. The information at the top of page 28 of section 4 introduces the concept of the procedure very well. So, use this introduction in the exam if you are unsure of what the procedure entails. Below the introduction is the detailed methodology of the procedure itself. Part of the calculation for the increased V2 procedure uses the graphs which are shown on the following 2 pages. The third additional type of procedure is probably the most common, and it is referred to by many different names. It is detailed on page 31 of section 4 in Cap 698. This third procedure is referred to as the reduced thrust takeoff, variable thrust takeoff, or assumed temperature takeoff. However, Airbus uses the term flexible takeoff. At the top of the page, it states that the main reason for doing this procedure is to preserve engine life and also help reduce noise. The procedure can be used at any time the actual takeoff mass is less than the maximum permissible takeoff mass and that there is an available distance that greatly exceeds that which is required. The maximum reduction in thrust from the full rated takeoff thrust value is 25%. Below this introduction is the restriction list to the reduced thrust procedure. You will be tested on this restriction list in the exam, so ensure you're familiar with it. Although not strictly part of the list, it would be unwise to carry out a reduced thrust takeoff with wind shear conditions, either forecast or present, because when an aircraft is struck by wind shear, full power is usually needed and fairly rapidly. Towards the bottom of the page is the instruction on how to calculate the reduced thrust takeoff procedure. Essentially, this procedure involves pretending or assuming that the temperature is a lot hotter than it actually is. Imagine for the moment that the outside air temperature was continually increasing, and as a result the thrust produced by the engines continually decreasing. There will eventually be a temperature beyond which there is insufficient thrust to complete a takeoff. This temperature is then used as the assumed temperature, and the thrust equating to this temperature is then set as the takeoff thrust. The last additional takeoff procedure is used when the anti-skid system is inoperative. You may think that this is not important for takeoff, but bear in mind Class A aeroplanes have to demonstrate that in the event of engine failure, the aeroplane is able to stop within the confines of the runway. Therefore, the accelerate stop distance required must be less or equal to the field available as shown. If the anti-skid system doesn't work, then the stopping ability will be severely reduced and will cause the accelerate stop distance to increase dramatically. To solve the problem, V1 is reduced. You may recall that reducing V1 decreases the accelerate stop distance, but the side effect is that it increases the takeoff distance. To resolve this, the mass of the aeroplane is reduced, which will decrease both the accelerate stop distance and the takeoff distance required, so that they will now remain within the available field lengths. In summary then, with the anti-skid system inoperative, V1 and aeroplane mass must be decreased. The anti-skid inoperative procedure is detailed on page 34 of section 4 in CAP 698. At the top of the page is a very clear introduction to the procedure, and below this is the method for calculating the mass and V1 reduction. This completes the lesson on the Class A takeoff performance. The takeoff requirements for Class A are very detailed, and there is a lot of information to take in. Concentrate on understanding the V-speeds. These are important, not just for the exam, but for the rest of your career as a professional pilot. Misunderstanding them and miscalculating them can have catastrophic effects on the aeroplane's performance. Be careful to correctly calculate these speeds, and just as important, insert them correctly into the flight management computer. There are tolerances in the system which will alert you if these speeds are not entered correctly, but these tolerances only highlight large abnormalities. Small ones will not be highlighted to the pilots. Concentrate as well on the limiting masses. Understand what they mean and how they are affected by the airplane configuration or environmental conditions. Most times, these masses will be worked out for you by the operator, and the masses will either be entered manually or electronically downloaded via the ACARS system into the flight management computer. Check these masses are within the limits of the airplane's performance. If you are unsure and uncertain about carrying out these procedures straight away when you start your first commercial flight, don't worry. You will have undergone a type rating course to fully understand the specific performance of the aeroplane you will fly before you take your first passengers. Therefore, some of the performance principles and performance procedures will be covered again at a later time.